Um, Good afternoon, ladies and gentlemen. It's wonderful to be here with you today. My first GeeCON. I'm excited to be here. And I'm here to talk about testing. But before I start, allow me to introduce myself really briefly. My name is Jan Stępień. I'm based in Berlin, where I work at InnoQ. We're a consultancy. And as a consultant, I help people build better software, sometimes as a software developer, sometimes as an architect or a trainer. Enough about me, let's talk about you. My goal for today is to make you better at testing. I'm sure that you write excellent tests, and I want you to keep writing those tests. I want to give you another tool, another very interesting tool which can help you tackle those most difficult cases, those really special systems under test which require particular attention. But let me start with a general question. Why do we test in the first place? Because we don't need to, but we do anyway. One could say that's because of quality of the software we build, but I think that's nonsense. We can manually go through user stories, click through the interface, and see that the database produces the right results and saves right data, and the quality is there. But we don't do it because we don't have time. So in our case, testing is all about automation. We want to automatically get the same assurances, but without any human input. And we automate so many things already, right? We automate our builds in our CI pipelines. We automate our provisioning with Terraform, Ansible, you name it. And then finally, using continuous deployment, continuous delivery, we automatically push all this stuff to production, and it just works. And it does so, among other things, thanks to testing. And just like Fred George said yesterday, the day before, you won't deploy 600 times a week if you don't have all those steps automated and taken care of, right? This is a prerequisite. And tests belong to this group. So let's talk about this story of automation and maybe quality. Keeping Slido in mind, I would love to have your questions. So ask questions, upvote questions of others. And yeah, let's talk about fitness tracking. This is our system under test. Back when I was running a lot, I used to have such a thing. And this is what I call business logic. It's not a whole lot of it. It's a very simple case. I'm using naked numbers. But we ended up with such a function, and now it's our task before we start, say, refactoring, for example. We need some tests to make sure that the existing behavior remains in place and nothing falls apart. So we can write a handful of tests. For example, those 3 points might be good enough. I'm ignoring the divide by zero case because it's not really meaningful, so it's not a behavior we want to test for and explicitly preserve in the refactoring. So we look at those 3 cases and we're like, this might be enough. And if it's not, how many more tests would we need to be certain that our system is sufficiently well tested? 10 more, 100 more, 1,000 more? It's difficult to say. And also, what led us to those particular values? Are they special in any way, particularly interesting? Did they literally appear in user stories? Let's move things around a little bit. I extracted all the values into a single collection, a single table, a list of inputs and expected outputs, and then the assertion is completely decoupled from actual values. They're fed from outside. And now with this thing, I want us to take a step back and talk to a domain expert in the world of fitness tracking to gain a better understanding of what we are actually testing. And our domain expert will be our primary school math teacher. A over B equals A over B. If we multiply both sides by B and then simplify the right side, we end up with the following property. It's a keyword for today. That's a property. We got it thanks to a conversation with an expert who knows the domain better than we do as software specialists. And now we can take this property and put it in this piece of code we wrote before. Notice what's changing. Something has changed inside of the assertion, that's cool, but what's far more interesting is the fact that we don't need return values of this function anymore. We don't care what those return values are. We just keep feeding inputs, and for arbitrary inputs, we should always see this property being satisfied. So what would prevent us from generating more and more completely arbitrary inputs, hopefully exercising various exciting edge cases, and see whether the property holds for all of them? And exactly this reasoning, this approach is called generative or property-based testing, where we subject our properties to large volumes of automatically generated inputs. The approach is 20 years old. It was published in 1999. The library, the first library implementing it, was called QuickCheck. It comes from the functional programming world, but it quickly moved to other domains and got implemented in other programming languages. In Java, we have at least 2 libraries. In the world of Java, we have at least 2 libraries implementing this principle. Let's take a look how this property, this assertion, would look like when expressed in those libraries. The first one is JUnit QuickCheck. It looks like nearly like normal JUnit, but instead of having this @test annotations, we have those @property annotations. And it looks a bit different because those functions have parameters. And thanks to this property annotation, the test library, the test framework, generates values having read types of arguments, generate arbitrary values of those types, and feeds them into our function, running it, I think by default 100 times, but it's a configurable parameter. So if you want to be really sure, you can just run it overnight on your CI. That's one thing. Another library which I like a lot because it's a bit less annotation heavy and more explicit and reads like English is Quick Theories. It looks like this. Using Quick Theories, we can say for all integers, which are positive, and for any double, check that the following holds. And it's exactly what we wrote in plain English a couple of slides before. So we see we have built-in generators of value simple numbers. We have also generators of strings, and we can say, I want only ASCII strings, or I want alphanumeric strings, or some very exciting strings with all the OGonics you can imagine. And now let's run this test against our function. And we end up with an error, which is not all that surprising, right? If we zoom in, we see that it's an assertion error. With something, the assertion of the equality check has failed. And we see those 2 values which were fed in the function which led to the problem. 1 and 0 is the smallest found falsifying value. For those values, something doesn't work. We expected 1, we got not a number. Well, we can't change mathematics. All we can do is either work with our system under test or our property and try to somehow narrow it down so that it generates values only within our domain, values legal in our world. So let's return to the property and take a look at this generator of doubles. It's not any double, it's any double which is not 0. After a chat with our domain expert, we decided that a 10 is a good value to begin with. Nobody wants an average for less than 10 seconds of steps. So with 10 in place, we can say that we want all doubles between 10 and 1 million, for example. Or an alternative approach, we can return to the previous version and add a call to assuming, which takes a predicate. Given 2 values which are generated, it says, yeah, those values are okay. Or it says, no, we need to generate other values because those, for any reason, are not something we can run the assertion on. And this way we narrow down the domain, in this case domain of doubles, to what we need. Now we run this again, quite certain that this time the assertion holds, because why wouldn't it? Well, it doesn't. And our testing library very quickly found some very exciting values, specifically 10 a tiny bit, for which the equality doesn't hold because 1 is not nearly 1. And at this point, well, there's not much we can do, right? We hit something as fundamental as before. If we fire up our browser console and add two numbers, we realize that computers and mathematics have very different understanding of addition. And there's nothing we can do. We just have to, again, work with our property and say, well, maybe a more accurate, maybe a better check would be, say, falls within certain margin of error. And this way we keep working with our properties, making them actually describe as accurately as possible the domain we're testing. And we already see several new degrees of automation. We don't have just automatic execution of tests. We have automatic generation of values which our properties will be subjected to. And also automatic generation of edge cases. Because we as humans, as developers, are really bad at testing our own code. We are too optimistic. We need somebody to tell us there is something in between you haven't thought of. And this tool excels at it, automatically finding mean combination of inputs which might result to falsifying our assumptions. But testing is not only about automation, right? Those of us who do test-driven development know that testing is also about design. Having our tests drive us towards an elegant design of the software. And property-based testing can be also very efficiently, very effectively used for test-driven development. Let's consider a different example, also a very simple one. Reversing lists, and by lists I mean immutable lists, with my regards for Grzegorz Piwowarek. If we want to test this, if we want to test drive an implementation of such a simple function, we would also start with a property. Let's start with lists of longs and think about the property which will hold for all lists of longs which are between 0 and 10 elements. What would we check for? What kind of property holds for reverse? There is no single right answer. There are several good ideas. What I'd like to begin with is the fact that if we reverse twice, we get the same thing back. Right? That's a very nice cycle. It looks silly, but it's quite valuable because it already conveys the fact that reverse must preserve all the elements of the list in between calls. Right? Just two calls, just one assertion, but already quite meaningful property. Let's implement it. Our test, well, is completely red because there's no code, but let's make this test green by implementing a valid version of reverse. So we have an entirely wrong function which fully satisfies our properties. So we need to continue narrowing it down. Think about another property which would make sure that this is not legal. Another thing which I thought of is the fact that if you reverse a list which is not empty, the first thing becomes the last thing. So we can express it like this. If we have lists of size between 1 and 100, after reversing, the last thing is equal to the first thing. And it turns out that if you add this property and run the code, it's surprisingly difficult to write such a reverse function which is invalid. But let's run it first. And we see that our testing library has found a falsifying case, and look how simple it is. It's just 1, 0. It's an example of a value and input list which falsifies our assumption. But it's not the only example value which our test framework has considered. If we scroll down, we will see that a whole lot of other values were considered. The one at the bottom is the one which the test library stumbled upon and said, oh, this is the first thing which doesn't satisfy the property. Or, in fact, all the properties we have here. And it said, well, I can give you just that, but instead of giving you something which might be large and difficult to interpret, it begins to reverse the operation of generators and begins so-called shrinking. It reduces the magnitude of all the inputs, so like making lists shorter, making numbers smaller, making strings simpler, and tries to generate a minimal example which still breaks your assumption, which breaks your property. Which is, again, automation is exactly what we would do. When we stumble upon a problem, we try to think, okay, so what actually in this piece of data and the state of the system has led to the problem? This tool automates this process, trying to find it for us, and then it gives us 1, 0 as a result. This is the minimal thing which breaks your assumptions. And that's something we can work with. It's not as impressive when we're working with lists of ints and longs. But consider the fact that given simple generators of numbers and simple generators of strings, we can combine those and generate arbitrarily complex data from our domain, like say a customer which is making an order in our shop. When you look at it, and after you serialize it as JSON, it's just strings and numbers. Some strings looking like dates. But in the end, it's all plain data. So by combining generators, you can generate arbitrarily complex instances of objects from your domain and then subject them to various properties discovered together with your domain experts. And I think since we already stumbled into the world of e-commerce, allow me to bring an example. A while ago, I worked with a German e-commerce website. And as customers browsed the catalog, browsed all the products, they ended up on those pages with those complex addresses representing all the potential filters you can apply to the databases. And then those URLs were parsed into objects representing the query which will be then sent to, say, Elasticsearch. And the logic for, first of all, parsing those URLs into filters to apply to the database, but even more so, for generating valid URLs, this was source of regressions, endless complexity, and problems. And there was a lot of stuff going on there because we had both like your standard complexity of mapping one structure to a string representation. We had all the constraints and requirements from SEO department, which had very clear vision how those URLs should look like, which ones are legal, which ones are not. And then finally, this website was running in a couple of countries, so we had it all internationalized per country. We knew we need to rewrite this module. It wasn't clear how and what to begin with because there was no reasonable test coverage. So we decided, okay, before we start the refactoring, we have very solid coverage of this system. And this is when we reached for property-based testing. So we looked at the problem and see, okay, what kind of property can we discover, can we express using our property-based testing libraries? And the property is here on the screen. And you've seen it before. It has something to do with the reverse function. If you generate an arbitrary, valid descriptor, the object on the bottom of the slide, you generate a string out of it and you parse the string again, you have exactly the same object. So we have this cycle again. And what we did, we expressed exactly this property that for all arbitrary search filters descriptors, if you generate a URL and parse it, we have equality check. And this single property has been an endless source of code regressions, fixed bugs. It helped us immensely during the refactoring. And we even were able to come to our colleagues from the SEO department and say, we can't implement it, we're sorry. But given this requirement and this requirement, we have this specific data structure, this specific search, and we see a conflict, that those two are mutually incompatible. This was just fantastic. And also the understanding of rules our colleagues which work with the domain defined, and the test framework which assisted us in encoding those rules, and also how it drove our implementation. We started with a minimal generator, which generated just simplest possible search terms, search data structures. And as we got this thing right, we kept adding more and more complex generators, leading to discovering various interactions between parts of this logic. It was just an excellent experience. And this leads me to calling this practice, this property-based testing, an excellent, maybe not replacement, but something which accompanies test-driven development very well, where you drive your tests, where you drive your implementation using properties. This leads not only to better design, but also to a better understanding of your domain. Because to come up with a couple of examples and encode them as a single example-based test is relatively easy compared to how much you have to invest in terms of time and understanding to work with your colleagues and define and find general properties spanning the entire system. You understand the domain you work with far better through this thought process. Okay, very well. So we've already seen some basics, some principles. And as we keep Slido in mind, let's notice that so far we were only looking at systems which, well, are far away from, so to speak, real life. There is nothing moving inside. There is no change happening. There is no time affecting the system, no mutable state. There is no real change of the state happening. Can property-based testing assist us in testing stateful systems which change as time passes? It turns out they are the property-based approach is surprisingly effective at testing such complex systems. As we discussed, we can generate arbitrary instances of our business entities, of our domain objects. And if we can generate those instances, we can also generate events describing change to those instances. Think of all the event-driven architecture talks and keynotes we've had so far. We can generate an event which describes something has changed to your system, and if we can generate a single event, we can generate sequence of them, apply them to the system, and see whether the system satisfies our property, satisfies certain criteria, depending, for example, on the ordering of events, or the fact that when one event got executed, another one suddenly cannot be reliably executed in the same way had that previous one not been there. Let's illustrate this approach with a, again, simple example. Let's implement a facade for Redis, a simple cache where we can save some data and get some data with just a handful of operations. Setting a key, getting a value under that key, deleting a key, and clearing the entire cache. In order to encode those operations as data, we need to somehow encode the idea of an operation and then simple classes, simple plain old objects describing those changes. So we have an operation, and then a set class, which sets a given key at a value, given value at a key, get, allowing us to obtain it, deleting a key and clearing the entire database. And using generators of sequences, generators of strings, we can generate arbitrary instances of those operations as well as entire sequences of operations which will be executed. And then we need some sort of interpretation mechanism which will take those sequences and interpret them, run them against our system under test, against our class with a Redis backing it somewhere far away in the network. And now the Redis is in some state after this run, and those operations brought some results, returned some values. What we need now is an oracle. And by oracle, I mean this medium, this person who stands between us and divine entities whom we can ask, is our implementation rubbish? And we run our tests, we run our sequence of operations against Redis cache and our oracle being Java util hashmap. And hashmap is a simplified but fairly correct model of the system under test. It models it without all the complexity, and we can trust it to be correct. Right? We run both versions, and we define certain post conditions. For example, every single operation has to return the same result as it does against hashmap. And if it doesn't, then the test fails and shrinking begins. And the test framework begins to shrink and simplify our sequence of operations, yielding the smallest possible sequence, leading to a problem. Right? Automation of debugging a multi-step debugging process of a complex system. If you want to learn more about this approach, I heartily recommend this presentation, Testing the Hard Stuff and Staying Sane. John Hughes is one of the authors of property-based testing and works a lot with this method. He has founded a company which is providing services around property-based testing and speaks a lot at conferences. He's a brilliant guy, and his talks are entertaining because he takes examples from the industry, and they're frightening sometimes. He's contracted, say, in this talk. I don't want to spoil too much because it's a good talk, but he is describing a contract where they were testing internal communication bus in cars, in automotive industry, and they discovered that the protocol connecting various subsystems of a car, and there's a lot of them these days, have problems with prioritizing messages. So you really, really shouldn't fiddle with your volume as you're braking. It's just beautiful. And it's all thanks to tools where various sequences of complex operations are ran against such a massive system and then minimized to very real problems. Yeah, so watch this stuff and watch other things which John Hughes has to offer. And in the meantime, we talked about state, right? State is exciting on its own, things are changing, the system is evolving. But state becomes really, really interesting when it's concurrent and multi-threaded. And this is when things get really complex, because we have absolutely no idea what is going on. And this might lead to deadlocks, this might lead to unexpected values, this might lead to race conditions, problems which occur when actions executed concurrently aren't isolated from one another and affect one another, where a sequential execution of actions wouldn't lead to a result which we have observed in a concurrent environment. And again, a question, can property-based testing help us testing concurrent stateful systems? Well, let's think at what does it mean to have a concurrent stateful system. It means that we have, for example, two threads, the Greek thread and the Arabic thread, and they execute 4 operations each at the same time, concurrently. We have no idea what the order will be. We have a single system, for example, a Redis cache, and we execute all those operations from 2 threads. The system ended up in some state. But we know that if those operations, if those 2 threads don't have any impact on each other, don't affect each other's execution, the resulting state should be the same as if those operations were executed in some interleaving. That is, individual subsequences are preserved, the order is preserved, but we don't know how individual threads interleaved their execution. I hope everybody's following me so far, because it's getting more exciting. So we have our case with 2 threads, and we put those 2 sequences of operations we generated with our framework, put them into 2 threads which are waiting behind some kind of lock, and then we say, go. And those 2 threads execute those operations, and something happened, and we ended up in a state S. Our Redis cache is in a state S. Those 2 threads yielded values, we can call them S. And now we know that if there were no interactions between those 2 threads, then those operations were interleaved somehow. So S must be either the result of execution in this order, or the result of execution in that order, or many other possible orders. This quickly gets, the number very quickly gets big. So we know that sequential executions have brought us to those, in this case, 9 states. In practice, many, many more. And if S is not a member of this state, of this set, if we can't find S among sequential executions, we know that the result of the concurrent execution has been affected by the concurrent environment. That there was some kind of race condition, some kind of interaction between those threads, which led to an unexpected result. And this is again something which John Hughes talks about, just like testing stateful systems, testing next step concurrent stateful systems. And it's fascinating because he shows in another talk of his fascinating examples of complex systems such as thread pools in distributed databases, which depending on certain interleaving of operations yields inexplicable results. And with tools such as these, you can find those cases. Of course, one important thing is we have to remember that we're dealing with non-determinism. We have no idea whether we will see that S ever again, because there's a chance that such a interleaving of threads, such decisions of our CPU scheduler will never happen again. So when we begin to shrink those sequences of operations, what happens if, for example, in the next step of shrinking, we will never see the same sequence again, we will just never see the same problem again? Again, what John Hughes advises here is simply just run the test 10 times. And it's more than likely that one of those executions will manifest the same problem. On JVM, JVM is a wonderful beast, but it has certain limitations. For example, we don't really have such a fine-grained control over threads and their execution as on other platforms. For example, if you work on top of the Erlang virtual machine, you can control threads at a far finer level and actually force the virtual machine to perform certain interleavings of those threads, which makes this process far faster than running it 10 times and hoping that it will work. But still, in any case, we're standing on shoulders of giants. And I'd like to illustrate this approach with another example. Who here knows Jepson and Kyle Kingsbury's work? I see some hands. So this is just brilliant. Kyle Kingsbury is a man who is grilling databases. So what he does is he takes some kind of distributed database we all here know and trust, and he reads carefully the documentation of this database. Specifically, what happens if problems occur, if networking problems occur, if there are glitches, if suddenly half of your cluster is disconnected from the rest. And then he reads the guarantees which authors of the database offer in such conditions. And then he replicates exactly those conditions in his test cluster, which he has full control of because it's a bunch of virtual machines. And he injects glitches into the network connecting database nodes. He's injecting delays, other problems, half of the cluster is invisible, and so on. And then just generates sequences of simple operations. And looks whether the result after the partitions are healed, after the database is back in a stable state, whether whether contents of the database can be explained by what's there in the documentation. Kyle has given a number of talks and wrote some excellent, very deep technical articles about various databases I don't want to name, but you know them and you use them. And I can only recommend reading those and realizing that, well, sometimes we have to trust, but sometimes we should well, also verify. It's really fantastic what is happening. What such, in principle, simple methods, how far they can bring us. Because this is, of course, nowhere as powerful as a formal proof that something is correct or not. It's just firing random tests. And more often than not, you find problems which occur in such settings. My friend, I want you to be better at testing. Your tests as they are, they totally work. But keep in mind that if you run into some really complex problems, really demanding, challenging systems under test, there are tools for that. There are tools which allow you to automate not only testing itself, but also generation of various mean inputs to your logic, but also automate the process of reducing those failing cases to a minimal thing you can work with, you can debug. It's not 5 kilobytes of JSON. Good luck, debug this. No, you have a minimal thing, and you know that everything in this thing had somehow impact on the invalid state of the system. And as Daniel Librero told us in his talk just yesterday, right? Automate all the things which computers can do for us. And this is such an excellent example of things which computers can do for us with advanced enough tooling. And also keep the design in mind. The fact that simple properties, few properties can already narrow down our design and help us implement elegant systems just like we would do using using test-driven development. But in this test-driven cycle, as we write a property and a simple generator just covering a small chunk of a domain, we hope we got our implementation right, and the property says, no, here's another example, now fix this, now fix that. And we have more and more things to work with. And once the test is actually green, we can switch to a different property or expand the scope of our generator covering the larger chunk of our domain. And all those things, in the end, taken together, finally lead us to quality. But quality is not a direct result of testing. It's a consequence of a number of choices around automation, around design, around choice of tooling, which, for a given case, can allow us to really speed up the testing and verification process. Okay, my friends, if you have any questions, I have an email address. I'm on Twitter, and if you need any other links, they're all at my website. So if you haven't written any questions on Slido, just shoot them over there. I'll be more than happy to get back to you later. And with this being said, this is all I've got. You've been a wonderful audience. Thank you all so much. So command tabbing out of it should bring me to the browser. Like here. Is Spock support available? I didn't know. That was fast, wasn't it? I'm so sorry. The second framework is JUnit agnostic. Sorry, I'm just repeating what you said aloud. Thank you so much. So we have an answer from the audience. Yes, the second framework is JUnit agnostic. You can use it anywhere. Go for it. Use it with Spock, blog about it, open source it. We need it. Don't you think this kind of test input generation approach may affect readability of testing code itself? It's a valid concern. I agree. Suddenly, we have the complexity of our tests grows because we do so many things in our tests. How can we, maybe we need to structure tests differently and write them in plain English saying, given arbitrary customer. And in the background, we have a helper which calls a generator and feeds a customer into it. Then the following holds, and then you have your assertion. I think there are tricks which allow you to make the code more readable using some DSL you build around it in Java or any other language. But it's still complex, right? We still have to deal with a degree of extra complexity in our tests. And at some point we might need to test our tests or verify that, for example, all the values we generate from our generators satisfy our validators, that we can verify, yes, every value we generated is actually a valid instance of customer class. And in the most extreme scenarios, you have tools to verify whether your tests make sense, such as, for example, mutation testing, PI test, tools which allow you to introduce random changes to your system under test and see whether your tests actually catch those synthetic problems. And maybe this way you can realize, oh, what I thought was working, what I thought was testing, actually tests nothing. But that's a material for a completely different presentation. Where was I? I answered the one on the top. Can we use it as external APIs? External APIs. Is the name generate? Scream yes if that's what you meant. I'm assuming that you mean that I have some kind of remote service, which is, in the worst case scenario, a network hop away, and I have to somehow speak to that thing? Or do you think external API as in I have a black box, a library or something, and I can test it locally, but I have no control over it?
External service.
External service.
Some other team does some external service in the company, and we just have to integrate it.
So it's a black box to a degree, right? We have no idea what we are testing, but maybe we can still talk about certain properties which it will always hold, even if we don't know what's happening inside. Maybe we can talk to them and ask, hey, is there something which we should check for, which always holds for this service? And another problem which I see there is the fact that if it's, for example, a network hop away, we are generating a lot of test cases and we have to run them over a network, so it slows the whole thing down. In this case, given the time constraint and how long it takes, maybe it would be reasonable to just run a handful of those tests locally on a developer's machine, and then, to be sure, run the rest overnight on continuous integration. And then over morning coffee, you see, okay, 10,000 inputs, everything is fine, good enough for me. Yeah, keep your continuous integration in mind. It's also an excellent place, for example, after a very big refactoring, you refactored some complex module, and you want to see whether the refactoring led you to a happy place. Notice that you have an oracle. You have an oracle for free. You have your old system, which is still there. It worked, hopefully correctly, so you can generate random inputs, run them against both systems, and verify that they behave the same way. And if you want to be more sure than after 100 of tests, you just let them run in CI for a while. And then hopefully you're certain enough. Where are we? Doesn't this way of... Yes. Oh, thank you very much. Is property some kind of invariant, or it's a different thing? Yes. In this case, we're talking about exactly the same idea. Invariant property, something which is always true, irrespectively of individual parameters. We're talking about the same thing. Still at the top, yeah. Thank you so much. It doesn't. Non-predictable. I won't return to my slides, but I forgot to point your attention to one thing which I had at the bottom of the slide. This approach has the random factor in it. We are not sure whether we will ever see the same sequence of inputs again. But at each execution, at each failed execution, we get a random seed, which we can then give back to our tool and say, please generate exactly the same sequence, and this is the random seed we had during the previous execution. And this way, the test framework will generate exactly the same sequence, and you should hit exactly same values if for some reason you want reproducibility. What you can also do is take those individual values which failed and you fix them as part of your standard example-based regression test suite. That's also fine. Property-based testing as a source of, as an exploratory method for finding some regressions in your code. Totally. That's yes. Okay, ladies and gentlemen, thank you all so much. It's been a pleasure.